Many of the current policies are about strengthening K-12 math teaching and learning, but for example, by evaluating teachers based on their students' achievement on high-stakes assessments. That's a core part of the No Child Left Behind law, for example. And so I think it's important to ask, well, can that work? Will that work? And I'm going to argue that there are really good reasons why that approach is unlikely to be effective. So I want to tell you a little bit about research on motivation, and this is not my area of expertise or research, but there is a big body of literature out there about this, and it's been around for a number of decades. And so some of it that I've read, it includes syntheses of many decades of research, including meta-analyses and handbook chapters, and so these are things that get pretty good scrutiny and get examined pretty carefully. And I think we can say, at least from my reading of it, I think that there are some results that are known from this line of research. So, let's just read this quote here. It says, "It is well established that the use of salient extrinsic rewards to motivate work behavior can be deleterious to intrinsic motivation and can thus have negative consequences for psychological adjustment, performance on interesting and personally important activities, and citizenship behavior." So salient extrinsic rewards, that's stuff like your students have performed at a certain level on a test, and therefore, that's the rewards. But notice, that can be deleterious and have negative consequences for performance on interesting and personally important activities, which I think teaching, any kind of teaching, really ought to be, and is for those of us who care about it, and I think for really all teachers. Now another quote, and this is about the specific theory called self-determination theory. That research, and again this has been around for a number of decades, that research has found that motivation based on more controlled motives, such as rewards or punishments, or self-esteem-based pressures, is associated with lower quality of learning, lessened persistence, and more negative emotional experience. Lower quality of learning. So one of the things we're after in teaching is higher quality of learning, not lower quality of learning. So if motivation is based on controlled motives, rewards and punishments, how well you've done or not done, or your students have done or not done on tests, that's going to have likely to have negative consequences. Lessened persistence, lower quality of learning. That's not what we're after. And again, another quote, "Pressures from schools, communities, and society for teachers to be more accountable for students' achievement can lead teachers to be more controlling and thus can be counterproductive for the goals of conceptual understanding and personal growth." Again, we want conceptual understanding. We want personal growth. These are things we're after in education. All of us, right? This is what we want for our students. But the more you make teachers accountable for students' achievement, the more you're going to undermine exactly these things that we're looking for. It's surprising, but this is what this research is finding. You may have heard of Campbells Law. I think this is really interesting, and people quote this every so often. "The more any quantitative social indicator is used for social decision-making, the more subject it will be to corruption pressures and the more apt it will be to distort and corrupt the social processes it is intended to monitor." Right? So any quantitative social indicator, quantitative, numerical score, if you're using scores on your students' achievement tests, the more likely that is going to be subject to corruption pressures, and that's going to distort exactly what you're after. again, this is just exactly the opposite of what we want. And so and then the bottom quote, when test scores become the goal of the teaching process, they both lose their value as indicators of educational status and distort the educational process in undesirable ways. Right? So these are telling us that these approaches that we're trying to take by regulating teaching through test scores and through evaluating teachers by their students' performance on scores, this is unlikely to yield positive results. Not only that, it's actually likely to undermine exactly what we're after. I think this is really counterintuitive. It's truly counterintuitive because we think if we make the stakes high enough, that's going to motivate people to reach them. But this research is telling us that's not the case. That's not the way it goes. So if these kind of external regulations are unlikely to work, we can ask, well, what else might we do? How can math teaching become a vigorous, vibrant profession? What else is there if we're not going to regulate the profession by students' performance, by seeing how well teachers raise their students' test scores? What else might we do? Well, I think we might look to other fields like scientific research, for example. And we might look to other fields like medicine and law, for example. Those are other possibilities. But since I come up through math research, and I know that, that paradigm or that way of operating, I think it's natural, at least for me, to look at, well, what is it that's making math research, for example, and other scientific research so strong? Because, think about it. Nobody is ever going to tell you that math research in this country is not incredibly strong and powerful, right? Have you ever heard complaints about math research not being up to snuff? No, it's in fact, it's stunning. It's vigorous. People prove amazing theorems, and it's sort of unbelievable how the field progresses. Other scientific research, it's just stunningly productive. It's very vigorous. It's very vibrant. What is it that makes those fields so vigorous? And you could say it's the people, but now think about this. A lot of people who do math research also do math teaching. In fact, most people who do math research also do math teaching. So if it's the people, then why would they be doing really well in math research, but not as well? I think we have to admit that it's by and large not as well in math teaching, right? So I think it can't be just the people. There must be something else to it. And I think what it is it's the culture, it's the system, it's the way of operating. So what is it in math and science research? Well, for one, we have public shared knowledge, and it's vetted by the community, right? The community decides what is quality work. You publish things, and it gets scrutinized very heavily. It gets really looked at carefully. That's true in all of the sciences and in math. The work is discussed in depth. It's not just superficial. It's not just, idle chit-chat. There's in-depth discussion of the work. There are seminars. There are presentations. People really scrutinize what they're doing. They are thinking together. They are looking at the work very carefully. People are building on and extending each other's work, right? They're not stopping with, oh, we know this. They're continuing to think about it. They're building their knowledge. The reward structure, if you think about it, yes, we get evaluated maybe by a department head, but somehow that's not really the thing, is it? If you think about scientific research, it's really, the real reward structure is admiration of your peers is what really counts. Quality is judged by your peers, not by a supervisor, not by some sort of external evaluation. It is truly your peers and you collectively that is deciding on quality. And in evaluating each other, if you're writing letters of recommendation, you note features and qualities of the work. It's descriptive, it's qualitative. It's not, of course people do count journal articles and so on. They count those things. But nevertheless, the features and qualities are what's really, really key, I think. And innovative approaches are prized. And those are shared, and those are admired. Another feature, I think, is that there really is a high bar to entry. To enter the community, you have to get a high level of education, and you have to demonstrate accomplishment in that field. Not just sort of general IQ or something like that, or general achievement. It's accomplishment in the field that you're working in. I think that's really important. So these are three overall qualities that I've picked out. I think we'd all agree that these are important components of scientific research, and maybe they're not the only important ones, but something I want to note about those is I think these actually fit very nicely with what research on motivation and development of expertise actually tells us is going to foster a very vigorous environment. Just summarizing from that research on motivation, internal motivation, what kind of, rather than external sort of pressures, is fostered by environments that fulfill the basic human needs for autonomy, competence, and relatedness. This is an outcome of the self-determination theory particular view of motivation, or that particular theory of motivation. Now think about math research, or math and science research. Autonomy is built into that because you pick your own path, you work on your own problems, you demonstrate your own expertise and excellence kind of in your own individual way. Competence, that's certainly built into the system. Your work is scrutinized. It is evaluated by your peers. It is looked at very carefully by your peers. And relatedness, that's about kind of having a community. Well, research communities really are communities. They're very tight-knit. They're very close. They discuss things very much together. So it's these features, these three central features of what foster internal motivation or foster very productive motivation are kind of built into the working life of research communities. And so based on this self-determination theory, it's not surprising that you would have very vigorous, very productive work done in a community that does this. This fits with that theory. And another thing we know, and I'm not showing any of the details about this, but there's also research on the development of expertise, and that points to the need to have deliberate practice over many, many years. You may have heard of these 10,000 hours, that kind of thing. So you need a system, if we're really going to develop expertise, you need a system that supports you over the long haul for many, many years to really hone and refine and build your work. So again, research on motivation, it's telling us work climates that promote the satisfaction of autonomy, competence, relatedness will yield the important work outcomes of persistence and maintain behavior change. Effective performance, particularly on tasks requiring creativity, cognitive flexibility, and conceptual understanding. I mean, those are integral part of math teaching. Job satisfaction, positive work-related attitudes, organizational and citizenship behaviors, and psychological adjustment and well-being. So this work is pointing us to say that it's not surprising that scientific research communities would be so productive, and also it gives you these other desirable outcomes. So what does this mean for math teaching? Well, could we develop a system or systems for math teaching that help us make math teaching strong and vibrant? And so in particular, could math teaching become stronger by developing a community that's has some of the features and traits of research communities that I noted, namely that develops public shared knowledge that's vetted by the community, not externally, but by the community itself, has a reward structure of peer admiration, and has a high bar to entry. I think that's exactly the kind of thing that we should be aiming for in math teaching. And so let me say a few more words about the high bar to entry, because that I think is one critical component. So there's the Mathematical Education of Teachers 2, MET 2, is a report that was published jointly by the American Math Society and the Mathematical Association of America in 2012. And that includes a bunch of recommendations on roles for mathematicians in teacher education. The reason I want to bring this up is because, again, I want to note that when we talk about improving math teaching, it shouldn't be just K-12, but it should also be the whole broader K through 16 or beyond that we need to think about. So in particular, mathematicians should recognize the need for improving math teaching at all levels. All who teach math should strive for continual improvement in their math teaching, and mathematicians should join with teachers at different levels to learn with and from each other. But now let me turn a little bit to the elementary grades. So the MET 2 document does talk about preparation for teaching at the elementary grades, and I think one important thing about teaching elementary math, it's so easy for people to think, oh, there's not that much to know to teach elementary school because it's, you know, it's elementary school and we learned all that and we know that. Well, I think a major advance, and this is what MET 2 says, a major advance in teacher education is the realization that teachers should study the math they will teach in depth and from the perspective of a teacher. There really is widespread agreement on that at this point, and I think that's a great thing. So the report recommends that before beginning to teach, an elementary teacher should study in depth and from a teacher's perspective the vast majority of K-5 math, its connection to pre-K, connections to grades 6 through 8. So, you know, for a lot of people that probably still seems like, well, how can you have college math classes on elementary school math and pre-K math and grades 6 through 8 math? But in fact, when you start looking at this material, and this is what I teach every day, every semester for many years, this stuff is much, much deeper than meets the eye. There's much more to know, and there's very detailed, specific knowledge that all elementary school teachers should have. And that's the kind of high bar to entry that I'm talking about for elementary school teachers. So one of the problems that we have currently is that future elementary teachers may enter college with only a superficial knowledge of that K-12 math, including the math they intend to teach. They may not know the rationales for computations with fractions or the role of place value in base 10 algorithms, and may not have had the opportunity to learn them as undergraduates. And that's a really big problem. We're sending people out routinely. We as a field are sending people out routinely to teach elementary school who just don't have an adequate preparation. They haven't thought through these ideas. They're not ready to teach it. And yet we are routinely allowing this to occur. And that's really wrong, I think. And I want to talk a little bit about some of the, just to give you a sense and a taste maybe of the complexity that's involved in teaching elementary school math. I'll say a few words about the Common Core State Standards. If you look at the K through 5 standards, they're broken up into what are called domains, and there's a domain on counting and cardinality, and some of these other domains that you see there. So let me give you a little task here. So so we're looking at the counting and cardinality domain in kindergarten, and here's a question basically for you about this domain. So let's say you you have a kindergarten student in front of you, or maybe even a younger child, and let's say that child can correctly say the first 5 counting numbers. So that child can say 1, 2, 3, 4, 5. All right, now that's not something people are born with. They have to learn that. So you have some young children who haven't reached that yet, but let's say that the young child can count 1, 2, 3, 4, 5. All right, will the child necessarily be able to determine how many blocks there are in this collection? So take a moment and have a little chat with your neighbor and see what you think.
Well, sure. Depending on the question.
All right, any comments about this? So any opinions or comments? None that anybody wants to voice? Oh, you're so brave. Yeah.
Just that there's a difference between being able to recite something
Yeah.
and being able to identify objects.
Yes, yeah. So actually one of the interesting things, children will first learn to just recite the list of counting numbers, right? And they may get that wrong at first. That's not an automatic thing. They don't say the numbers in the right order, or they skip some, and so on. So it's kind of a big deal, first of all, to just be able to say that list, 1, 2, 3, 4, 5, and then they learn to say it, up to 20, or first up to 10, up to 20, etc. All right, so that's a big deal. But that is not the same as saying how many there are. That's just this list. It's just a bunch of, it's like the ABC song, ABC, right? You're singing a song, you're reciting something. Not the same as counting how many. Here's what can go wrong. Did any of you identify some of the problems that could go wrong? Yeah, you did. Yeah. So what's going wrong here?
Double counting.
Yeah, there's some double counting. There's some skipping. So one way to summarize the problem here, all the different problems here, is the student is not making a one-to-one correspondence between the number words and the objects. Part of counting is you make a one-to-one correspondence between the words and the objects. All right? So that's one thing. Let's say that a child does know how to make a one-to-one correspondence, right? So that's not something obvious that we know from birth. We learn this. We learn to make a one-to-one correspondence. Let's suppose the child can make that one-to-one correspondence between the number words and the objects. Is that enough? Turns out that's not enough. Now, are you thinking about this? I mean, does everybody just know that these are issues that you need to know if you're going to teach kindergarten? Right? See how this is not obvious? This is kindergarten material. This is something every teacher needs to know if they are going to teach kindergarten. We as adults don't know this because we've already learned to count. We've forgotten that we didn't know, and we've forgotten how it is that we came to know how to count. So there's detailed stuff to know that every teacher needs to know, and they have to have studied this because they're not going to just know that on their own. So see, here's the example. So child 1, and this experiment has been done with children. The teacher asks, how many blocks are there? Both child 1 and child 2 make the one-to-one correspondence between the number words and the objects. And then the teacher says, oh, so how many blocks are there? And child 1 might just go and count them again. Child 2, on the other hand, realizes, oh, that's 5 altogether. So there's this other piece of knowledge that the last number word you say also tells you how many in all. That is not obvious. Teachers need to know this. This is a piece of professional knowledge that must be acquired, I think, before you're going to go out and teach elementary school. But you have to study it, and that means you have to have time to study it. And if you start looking at the body of material that you really need to have studied, it's a lot. It's substantial, and it's going to take a certain amount of coursework. The MET 2 recommends 12 semester hours of a specific content coursework for elementary teachers. And that's about right. And that's not including the methods. I wanted to say a little bit about teaching learning paths for young children. So I was showing you just a little tiny smidgen there of the counting and cardinality, which is part of sort of a bigger teaching and learning path for young children. So there was a National Research Council committee on early childhood mathematics. I was very fortunate to have been on that committee. It was a great committee to be on. That committee produced a report that's called Mathematics Learning in Early Childhood, Paths Towards Excellence and Equity. And that is based on many decades of research of young children's thinking. Very careful work into how children think about various mathematical ideas and how you can build from one idea to the next. And so based on all of this research, there are, the report laid out some teaching learning paths for young children, basically pre-K through roughly grade 1 or 2. And the Common Core State Standards at kindergarten through grade 2 actually really reflect those teaching and learning paths. So I know there's some controversy out there sometimes about the Common Core, but at least at these early grades, it's based on some very careful research done over many years by many different people that kind of accumulates the knowledge of the field about how we can teach young children mathematical ideas. These are things that I think that teachers should have studied. Not the detailed research, but the outgrowth of that detailed research, the teaching and learning paths. Actually I think I'll skip over this because I want to just show you one little tidbit, one tiny bit. This is a small piece of kind of a bigger progression, but I can give you, I think, a little sense of part of this teaching learning path that's involved for young children. So we all know young kids need to learn first grade, second grade, single-digit additions and associated subtractions, right? 2 plus 4, 7 plus 9, etc. And just to be totally clear, the Common Core definitely do expect young children to know those facts, those basic facts. The specific wording is know from memory, those basic facts. But there's a progression that gets you to that place. So the progression that gets you to that place is not just rote memorization. It's not just pull out flashcards and memorize. It is, there's a very, I think, very thoughtful and carefully worked out progression, and it's based on children's thinking. And it's broken up into 3 levels. So this, I can kind of give you a sense of that because of those 3 levels. So at the first level, count all. That's like if we're going to ask a kid to add 6 plus 3, the kids would put out 6 blocks maybe, and then 3 more blocks, and then count all of them and realize there's 9. And so that would be a count all strategy. Level 2 is count on, and then count on from larger, and then count on to subtract. And level 3 is a derived fact method. So I'll give you a little taste of levels 2 and 3. So this counting on, if we're asking kids what is 6 plus 3, to count on, a child might say 6, 7, 8, 9, right? So 6 plus 3 is 9. So see how that's an advance over just put 6 things out, put 3 things out, count them all. It's kind of taking that 6 as a starting point and moving from there. So the idea is to get kids from the count all to count on. Now another little advance within that level 2 is to recognize that you can apply commutativity. So if you ask what's 3 plus 6, the child can go, oh, 3 plus 6, that's 6 plus 3, and now I can either count on or I can already just know that fact. But this is a really crucial piece of knowledge because it's going to allow you to cut the number of facts that you need to learn almost in half, right? The commutativity allows you to cut them almost in half. And then here's another one, grouping by tens. This is a level 3 derived fact method. So if we're adding 8 plus 6, well, do you see what you might do? Put yourself in the shoes of a kid who's still learning those facts. You might think in terms of breaking that 6 into 2 and 4, and then combining the 2 with the 8 to make a 10, and then we have 10 and 4 more is 14. So the reason this is level 3 is called a derived fact method is because we're kind of going from 8 plus 6 to using other facts. We're breaking things apart, we're combining the 8 and the 2 to make a 10, and then we're using the fact that 10 and 4 more, that's 14. Now, why would one want to do this? Well, we work in base 10. That's a crucial part of the learning for young children. And so this is really emphasizing that base 10. It's emphasizing making a 10. If you think about what is 14, well, it's, and the way that we write 14, it's a 10 and 4 more. And that's a crucial piece of knowledge. So this, working this way, this is algebraic because it's applying the associative property, and it's also relating facts to other facts. We're relating, we're breaking numbers apart and we're putting other numbers together, and it's kind of working with in that richer, deeper environment where we're really thinking about what is base 10, what is a number like 14. Notice that we have to break numbers apart. So this is a crucial piece of knowledge for teachers. If you're going to use this level 3 strategies, you've got to know, okay, we're going to use an associative property idea, we're going to make tens, we're going to think of numbers in terms of tens and ones. We also have to be able to break numbers apart. If you look at the Common Core State Standards, there are problem types in the appendix, and some of the problem types include addition and subtraction type problems where you're taking an amount and breaking it into 2 different amounts. The reason for that is exactly so that students will have available to them this kind of skill, and that they'll be able to use this level 3 strategy. Yeah? So I'm going through all this, very quickly, but I want you to see that there's a lot here for a teacher to know, and I'm just looking at single-digit additions at this point. There's a lot of stuff here to think about. So let me give you another thing to think about. 13 minus 9. And again, put yourself in the shoes of a young child. They're still learning their single-digit facts. Eventually, they're going to just know their single-digit facts. They will have them memorized. But what are some methods? And think about a derived fact method like we were just looking at level 3. What are some methods that young children who are still learning those facts could use to calculate 13 minus 9? Again, take a moment, have a little chat with your neighbor, and see what you come up with. Any ideas? Anybody want to share an idea? Take 9 away from the 10 column, yeah. So that's one possibility. So in other words, we're really thinking of 13 as 10 and 3. And we could take 9 from that 10. And then that would leave 1 left. And 1 and 3 make 4. Yeah, so that's one strategy. And notice that's really, it's emphasizing 13 as 10 and 3. So that's a really nice thing. Did you think of any others?
13 minus 10 plus 1?
Yeah, 14 minus 10 plus, 13 minus 10 plus 1. So you subtract too much and then you add one back. Yes, so that would be another nice way, yeah. Anything else? Count down from 9 to 13. Yes, that's a great strategy because that would be emphasizing 13 minus 9 equals what is really the same as 9 plus what is 13. We know from some research that making that connection between addition and subtraction, I mean, well, first of all, even aside from any research, that's a crucial connection. Addition and subtraction as inverse operations is a crucial connection. But we also know from some research that young children who are taught to use that kind of strategy of viewing subtraction as unknown addition, an unknown add-end addition problem, that makes subtraction as easy for them as addition. And that's a huge thing. That's enormous for young children. So that's very important. So, and then there's other things you could do. But I just want to mention that, you might wonder, well, do we really need to go through all that for young children? Do they really? Why not just make them memorize it? That'll be good enough. Well, in addition to they're learning algebraic strategies, they're focusing on base 10, which is critical. But we also see high-performing countries like Japan and Singapore, they teach children these types of strategies. This is from a translation of a Japanese first grade book, and they are using exactly that strategy of subtracting from 10. Right? So this is what the high-performing countries, they're actually using, they are currently making use of the kinds of things that we know from math education research. They're making use of routinely, much more routinely in their instruction. So, and then there's other, I'll skip over there. So I hope I convinced you at least a little bit that there's a lot to know even at the elementary grades. Middle grades math, that is even way scarier because, well, so MET2 has recommendations, but it turns out that these MET2 recommendations, they're not coming close to being met. In the interest of time, I'm going to skip over some of this. But if you look at middle grades mathematics, that stuff is really crucial. That's the things that we're working on in the middle grades: ratio and proportional relationships, percent, linear relationships, algebraic ideas. From a report from the National Center on Education and the Economy, a very high priority needs to be put on learning this material much better. I'm not going to read all this. But if you look at the Common Core, there's standards, for example, about ratio, and it's asking for reasoning, not just set up a proportion, cross-multiply, and solve it. There's a lot of recommendations out there that's not good enough. That's not going to get the thinking skills, the reasoning that we really need for them to be able to use ratio, proportional relationships, critical ideas. So I've been doing some research with a colleague, Andrew Izak, at University of Georgia, and one of the things we've been doing is studying future middle grades teachers and working with them to see how they reason about the ratio and proportional relationships. And the reason for that is really we need more detailed knowledge about student and teacher thinking about these really crucial ideas. So let me, again, give you just a moment. Here's an example of a kind of task that we've used, and it involves a strip diagram. That's something that you all who've been using my book, you know those very well. I'll just give you a moment. How would you solve this problem using a strip diagram? So it's a proportion problem, but instead of just cross-multiplying and so on, how would you solve it? I'll give you a moment. You can chat with your neighbors. Any ideas on this? Do you have any strategies for this one?
Each block of copper is so many grams.
Yeah, exactly. So, and to find that, we see, oh, there's 23 grams, and there's 5 blocks. So 23 divided by 5 is what goes in each block. And then that times 7, if there's 7 up above, times 7. So that would be this strategy here. And this is something that we see our future teachers, it's a kind of strategy that we see them use. And we think this is the kind of thing that also young children, or 6th and 7th graders would be able to do as well. Right, so that's one way of solving that problem. Did you think of any others?
Add strips until they're even.
Yeah.
Add strips of 5 and add strips of 7.
Strips of 2 and make them even. Yeah, no, that's an interesting idea. And then I'm not sure how we would know what goes in each part, and then maybe you would divide by 2 or something. Yeah, you might be able to play around with that a little bit. Well, another thing you could do is just think about a multiplicative relationship between the two amounts. So that since the pure gold is 7 parts and the copper is 5 parts, the pure gold is 7/5 times as much, or 7/5 times the amount of copper. And so you're multiplying by 7/5. And in fact, we see this strategy also with future teachers. But notice one thing about this strategy, and actually the other one as well, but this turns very naturally into an equation for a linear relationship between the two quantities. If we think of the two quantities as varying, x grams and y grams, then we can make a linear relationship, in fact a proportional relationship, and this way of thinking and reasoning about the quantities relates them in that kind of equation. So developing equations, that's a really crucial part of middle grades math. So there's, if we think about what are some of the takeaways from this, there's a lot to know to be prepared to teach math. I just gave you the tiniest scratches of things, but hopefully you have some sense of the bigger picture there. To enter the mathematics teaching profession, teachers really should study the math they will teach in depth and from the perspective of teaching it. But our current system just doesn't ensure adequate preparation or professional development. Routinely, we have some amazing bright spots and wonderful things that go on in various cases, but it's not sort of system-wide. We know a lot from math education research about how to teach math effectively, especially at the early grades, but currently we often are not implementing what we do know. The system is just not designed to support putting into place the knowledge that we actually have. So we have a system, it's not truly professional. I think it's really not working as we are in its current configuration, but our current fixes aren't going to work either. So I think where we need to go is we really need this mathematics teaching community across all of our levels. We have to start seeing ourselves as a professional community. We have to start taking responsibility for math teaching at all levels. We have to decide that we decide what qualifies as appropriate for professional education and development. We're letting other bodies and organizations kind of do that for us at the moment. We're not putting our feet down about what it means and what should be required for us. We have to demand high standards for entry into our community. And we need a system that helps our knowledge develop and grow. We have to have repositories of shared and vetted knowledge. We should be competing for each other's admiration by sharing our ideas, the way people do in the sciences. And we have to use that kind of system to evaluate our work. We have to negotiate and promote excellence from within our community. This is our responsibility, and it's us who need to do that. We have to evaluate our work using qualitative, descriptive means, resist external accountability measures. We know those can't work based on research on motivation. We should not be allowing summative assessments to drive teaching. We need to have lofty visions about learning and understanding, and that should be what should guide us. So I suggest let's join together, let's advocate collectively to make math teaching strong. I think that's the direction we need to go in. And it's not an easy job, but I think that's where we have to go. So thank you very much. I'll leave these slides. I do have references if you're interested.
If anyone has a question, we have time for a couple of those.
Yeah.
I hear stories that people, for example, PhDs in science are trying to help their elementary kids with their Common Core homework and are baffled.
Mm-hmm.
Do you have any comment on that?
Yeah, well, a lot of us, came through math with a certain approach to it, and you don't necessarily know that the approaches that are being used. For example, I showed you these derived fact methods for addition. Well, even if you have a PhD in math, you haven't. Of course, everybody with a PhD in math will recognize what's going on there, but you won't have thought about teaching math that way, or thinking about it that way, or learning it that way. Same thing with the counting and cardinality. You won't know that there are pieces of knowledge there that your child needs to develop necessarily, because you've lost that in your background. So I think that's, that's why it's not surprising that stuff like that happens. And I think one of the messages that we as a community have to bring to the larger, broader community is that, there is this detailed, specific, professional knowledge that teachers should have, and hopefully someday that will be the norm and the expectation that all teachers do have that entering the profession. And that is not something that even a PhD in math necessarily has. It is a different body of knowledge. It's not the same thing.
So maybe the community should be broadened to have a handbook for perplexed parents.
Well, that would help. Yeah, that would help. Yeah, a handbook for perplexed parents. I like it. Yeah.
I was wondering how within a community, or if within a school, you could support teachers to do that way.
Mm.
To have the time to look at it and think about it and do that, because I know they're doing.
Yeah, teachers have
English and everything else.
huge demands. Yeah, so one of the things that has to occur is, there needs to be enough time for professional development, for thinking and working with others in teaching. And that should be built into the job. I mean, that's part of, if you think about research communities, it's built into the job that you're thinking about what you're doing. You're not just doing it, you also have to think about it. So I think that, and that is what other high-performing countries, Singapore and Japan, those teachers do have time to work with each other, and they have much more sustained professional development, and it's built into their working lives. We're probably, are we out of time? I don't know.